Today I'm going to review the SCA 300W power inverter. So after my recent car battery charger video, Supercheap Auto contacted me and they basically said choose some products from our online catalog and we'll send them to you to review as well. So the deal is that I'm going to be completely honest with these reviews and they've been very cooperative with that. That's totally what they're after as well. And then afterwards, after the review, I'll do a separate video which will be complete teardown, and they've been very cool about that too. So in this video we're going to go through the product. I'll take some measurements. I've got an oscilloscope and a car battery and some bits and pieces here that we'll set up, and we'll do a pretty thorough review and see exactly how this thing performs, and we'll look at all the details. So the first thing I'm going to do is take it out of its packaging and we'll see exactly what we get. So I just took the top off that, and hopefully this will now come apart. So we've got our instruction book, we've got some leads here, alligator clip leads by the looks of it, and of course we've got the inverter itself. You can see, like the car battery charger that I reviewed previously, there's different models for these inverters. I've got the one right down the middle, which is a 300W continuous power. You can see the specs there. It's a modified sine wave, filtered, and all the rest of the specs are pretty much the same. Basically, I've got some different output protection that just matches the rated power of the inverter. So I'm not going to go through too much detail. Looks like it comes with a 12-month warranty. It's got protection and low battery shut off and things like that. So that's all in that book. Here's the leads that we've got. They're nicely crimped and heat shielded. These clips look alright. Let me just... Okay, so the wires themselves don't have any identification. But they seem fairly sturdy. The clips on the car battery charger I reviewed were actually a little bit better than these ones, but we'll see how these fare. You can see just standard alligator clips there, and then on this end they've got the little crimped terminals there, heat shrunk, which is nice, and on the inverter itself you can see they got terminals there as well. So just to comment on these supplied leads with the inverter, they haven't given you the normal DC accessory jack or the cigarette plug style of jack. Reasoning is because they're generally rated for 8 to 10 amps in your car. This thing here is fused for 35 amps. So if you had this thing loaded up and plugged it into that jack, you'd blow the car fuse pretty much immediately on that circuit. So they've supplied alligator clips. So you'd plug that onto your car battery. You clip it onto your car battery, or if you've got a 4-drive with an auxiliary battery, you clip it onto the auxiliary battery, and that way you're not going to blow the fuse on your car accessory port. The other thing that you could do is, if you had this installed, say in your 4-drive, or you had it installed in some sort of camper situation, you could hardwire it in. You could run like a power feed from the battery out to this unit, whether it be in like some compartment in your car, or have it sitting there on the tailgate. You could do that as well. But that's cool. So that's the reason why you get alligator clips and not your normal DC auxiliary jack. So here's the inverter itself. You can see it's in this nice extruded aluminium case, and you can see they've got these little mounting screws across this side and another one over here. So that's probably where they're attaching the transistors to the edge of the case for heat sinking. So that's all nice. They've got some stats here on the top. Basically we've got 300W continuous, and I think it's 600W peak just for a spike, or for like inrush current and those sort of things. And we've got a 40 amp DC fuse on the 12-volt input here, and a low battery shut off at 10 volts. So if we look at the end here, this is where our battery terminals connect, and there's our fuse. So that's the 40 amp fuse, and we've got a little ventilation fan. So they're saying do not reverse input. I'm imagining that they would have reverse input protection, but yeah, you should probably heed that warning and just wire it up correctly, right? Now on the other side, we've got the power indicator, the protect circuitry indicator. So if it's in like a overload mode or something, I'm assuming that would indicate it there. We've got an on-off switch, and we've got our standard Australian GPO or power plug there. Now on the bottom, we've got all the standard sort of warning stickers and things. A few specs here, indoor use only. So these terminals here are pretty chunky and they're quite nice. I like the way that they've got these little partitions here, just to make sure that you don't get any sort of shorting out between the two, because that would be pretty nasty. I mean, it's 12 volts, but a car battery can put out a lot of amps, and shorting that out will, do all sorts of damage. You probably end up melting your cable. So that's why they've got that there, and that's that's good design, so that's nice. It looks like down here they're using a standard blade style car fuse. Let me just get that one out. There we go. Standard sort of blade style fuse, which is good. It says 32 volt and it actually says 35 amps. So at this stage, I've actually got a car battery here that I'm going to bring up on the bench, and we'll wire this thing up and fire it up. Alrighty, so as you can see here, I've got this car battery set up, and it should be fully charged. This one actually keeping a little solar panel out the back, and a little charge circuit. So you can see we've got 13 volts there. Okay, so I'm going to wire in these terminals now. We'll put that negative terminal in first. So they've labelled above the terminals, you can see we've got positive, negative, and obviously our black is our negative. And actually they also labelled it on the alligator clips themselves, so you can see negative there, it's sort of embossed. And you can also see the positive there on that clip. Okay, negative to negative, and positive to positive. And that's it. So it's switched off at the moment, but we should be able to turn that on now. Yep, you can see I've got some bright lights here, but you can probably see that power light's on there. And I might actually just measure that. By the way, I'm qualified to do electrical work up to 3-phase 415 volts. So I'm going to show you some measurements and tests now that you probably shouldn't do at home. But I'll do it for you basically. So you can see we're getting our 250 volts output there, which is cool. And this is 250 volts AC, and this is true RMS. Which would mean that we're probably getting about 350 volts peak to peak, positive and then negative. You got your AC waveform. As a matter of fact, I'll be showing you some more details about that later, because this is a modified sine wave inverter. There are also true sine wave inverters, and you can also get like cheap square wave inverters as well. So this one is sort of like in the middle, and I'll show you what that means, how it looks on a waveform, and the pros and cons of that depending on the equipment you're looking to run on this inverter. So we're getting serious when we bring out the oscilloscope. What I'm looking to show you is what we mean by modified sine wave and pure sine wave. And again, I just have to say, disclaimer, don't do this at home. As I said before, I've got a qualification to do these sort of measurements. And yeah, it can be quite dangerous if you're not careful or you don't know what you're doing. So with all that being said, let's get into it. All right, so let me just connect this to the mains here. So what you're looking at there is the 240 volt power out of the wall socket at my house here. So at the bottom of the screen, you can see we've got some measurements here. The first one is 245 volts RMS. So RMS means root mean squared. It's sort of like an average. I'm not going to go into that in a lot of detail in this video, but basically it's a good approximation of what the AC voltage is. Whereas your peak is what's happening right up here, and that's where we're reading the 345 volts. And then we've got peak to peak, so in the middle we've got 0 volts, then we've got our 245, and then we've got 345. So if you go down here, it's negative 344 volts. So our peak to peak voltage on the AC waveform here is 680 volts. What I really want to draw your attention to is this waveform and how it looks relatively smooth. You can see it's not perfect. There are some little lumps and bumps and things, which is to be expected on like a normal sort of mains power supply. But it's a nice sinusoidal wave. So you see it's sort of got that nice sweeping curve there. So what I'm going to do now is plug into the inverter and take a measurement of that, and we'll see how the waveform differs. Okay, so this is measured across the active and neutral of the output. And you can see how different this waveform looks. Now this is without any load, so I'm not drawing any current out of this inverter. It's just basically just the voltage at zero load. But you can see, whereas before we had that nice sweeping curve wave, this one here is stepped, and you see it's got like 3 different levels and it steps up and down. So this is what we call a modified sine wave. So it's an approximation of a sine wave. And to take it more basic than this would be like no middle step. You'd basically have a direct square wave. So this is sort of an intermediary between a sinusoidal wave and a square wave. But you can see again, we've got 253 volt RMS, that's all right. We've got 300 volt max, a little bit different now. This is just to do with the characteristics of the wave. And our peak to peak is 588 volts. So all of those values are quite respectable. There's nothing glaringly wrong with that. It's quite fine for what we're looking at. And the volts RMS is really what you'd use to rate this voltage. So we've got our 253 volt. It's a little bit higher than our mains power, but you can see the peak is actually a little bit less. So that's not really an issue there. You can also see that we're running at 50.66 hertz. So we're running slightly fast on the frequency. In Australia here we run 50 hertz for our mains power. Japan, United States is 60 hertz. But you can see this inverter is approximating that frequency. It's running a little bit fast, but generally that's not going to be an issue with appliances. So the obvious question now is, what are the repercussions of having a modified sine wave, this sort of stepped looking waveform, instead of the smooth pure sine wave, or the nice true sinusoidal wave like we saw in the normal mains power? And that really comes down to the application. What are you running off of this power? Now, if you can get away with running a modified sine wave, which you can in many cases, it's good to do so because it's going to save you a lot of money. Pure sine wave inverters are generally a lot more expensive. They're a lot more complicated electronics, so they run you up a higher price. Whereas the modified sine wave is a good compromise. It's not a perfect sine wave, but it can work in a lot of cases, but there are cases where it's better off going with a pure sine wave. So I'll run through a few examples. If you're running this on a pure resistive load, and when I say a resistive load, I mean something that's like a heater, like a element heater, like a light, like some sort of lighting application, and those sort of things. This is going to be perfectly fine. And you'll find that in most applications where you're not running big motors and things, this will be fine. So for things like a Peltier fridge or esky and those sort of things, for lighting, this is going to be not a problem at all. If you're running something like a refrigerator that actually has a compressor on board, this can still work, but just be careful because you'll lose efficiencies basically. Any motor, or when I say a motor, I'm talking about an inductive load technically. An inductive load really likes to have a nice pure sine wave. With it stepped like this, you're basically introducing inefficiencies, and that generates heat. So the motor's going to get a little bit hotter. It's going to use more energy by probably about 30%. And so you might have some thermal issues. It might sound a little bit different as well, depending on what you're running. So that's where you got to be careful. So I've changed up the configuration here a little bit. I've disconnected the battery completely. So we're now running the inverter here off of my lab power supply, which is a DC power supply. And that'll allow me to change the voltage. It's not connected at the moment, but you can see I can turn that voltage up and down. So we start somewhere around the 12 volt range. And then what I've also got is my Fluke multimeter over here. It's connected to the output and it's on AC voltage. So we'll be able to see what voltage we're getting out of the inverter as we modulate this input voltage. So there's a couple of things I'm looking for here. I'm looking at when I change this voltage, how much does it change the output voltage? The other thing I'm looking at is at around 10.5 to 10 volts, this should automatically turn off. That basically means that if you're running it off your car battery, it won't let it run dead flat. It'll get down to that 10 volt mark, which is still pretty low, but at least at that point, it'll turn itself off. So I'll be able to lower this voltage and see at what point it does turn off and make sure it is at a reasonable level there. So let's fire up the inverter and see what we get. So I'll connect power. You can see it's not drawing anything at the moment, which is good. So we've got a proper switch here. Turn that on, and we've got 247 volts here at the fluke, 248, and we're only drawing 170 milliamps here, and to be expected. So that's 0.1 amps, basically nothing, because we've got no load on the inverter at the moment. We're just measuring voltage. It's not drawing any power out of it. So this here is basically nothing plugged in. That's how much power it draws. It's like quiescent current, or standby current, you could say. So let's have a look at what happens. So we're now sitting here. We'll just let things settle a little bit. We're at 250 volts AC. Looks like it's fairly stable there. So I'm going to turn this up. We're now at 15 volts. And you can hear the inverter's fan just came on. It's blowing a little bit air at the back, so it's quite a noisy fan. And you can see the current draw went up as well. So I think that's basically the fan drawing that current. So it looks like the fan actually comes on when you're over a certain voltage, because I just dropped that and it turned off immediately. So if I go, I'm now at 14 volts. So it turns on at about 14.8 volts. That's interesting. And it turns off again when I turn the voltage down. Okay, interesting. In our next video where we do a teardown, we can have a look at that, because usually you'd have a thermistor or some sort of temperature sensor in the unit, and it would generally only turn the fan on as the unit heats up. You know, you've got a lot of load going through it. But let's turn this voltage right down now and see how low we can go. You can see we're sitting at 250 volts over here still. We're now under 12 volts. We're about 11.5, 11.3. Okay, we're at 11 volts. Still reading 250, 251, 252. We're now at 10.7. There we go. So it basically just squeals. But that was at 10.5 volts. So let me just go back down there again. We've got 252 volts over here. And it's still at the voltage. If I keep going. Yeah, you see it's turned off now. I'm going to kill the inverter. So it looks like around about 10.5 volts, we get the audible alarm come on. Then as you keep dropping the voltage down below 10 volts, it'll then switch off the output. I think the idea is that you get the audible alarm while you still got power, but it's getting low, so you can react and change your battery, do what you have to do. But if you do leave it and the battery does get lower in voltage, it'll switch off the output and hopefully save the battery. The output voltage only moved a couple of volts. You know, at 250 volts, it went up to maybe 252 and then down to 247 roundabouts. So I'm quite happy with that as well. That looks like it's regulating very well. Now we still haven't put any real load on this thing yet, so that's what I'm going to do next. I'm going to plug in some devices here and see how we go with that. So we're back on battery power now, and you can see I've got one of these little work lights. This is a 150 watt rated light, so it's half the continuous load that this can deliver. So let's fire up and see how we go. So you see it's driving the light perfectly. This is a purely resistive load, so this is an ideal application for an inverter like this, some sort of lighting situation. You may have noticed that the fan came on immediately that time. You feel it blowing air out the back there. Doesn't feel warm. This light feels warm, but the inverter doesn't feel too warm. I'll just let that run for a little bit and let it go, and I'll come back and check on it. Okay, so that's been running for some time now. It's still, fans running continuously. It's not getting warm at all. I'll just turn that off, just to kill that background noise. It is a little bit noisy, that fan, because it's quite a small fan, and generally the smaller the fan, when they're trying to get the airflow through, they get a bit noisy, but yeah, you can sort of hear, you can judge how noisy it is there. Okay, I'm now running a pretty ludicrous setup here. I just plugged in a power board and grabbed a bunch of devices I had at hand. So we've got a laptop over here, which is currently on battery mode, but when we turn it on, we should see that it starts charging and running off the AC power, off the mains power. I have a soldering iron here, which is 70 watts. I have the 150 watt work light sitting there on top of the battery, and I also have an inductive load. So this is a motor, this is just a pedestal fan, and all 4 of these devices are hooked up on this power strip, and you can see that that is plugged directly into the inverter. So I'm going to fire this thing up now and we'll see what happens. Hopefully nothing too drastic, but here we go. Alright, our lights come on. Our laptop is now charging, and let's turn the Hacko on. So we've got the Hacko fired up here now as well, so that's drawing 70 amps as it heats that up. And let's turn on the fan. That's it, I think that's what did it. Let's come back. Yeah, it's turning off again. So I think I am overloading it now, so I'm going to turn this fan off. You see, it'll turn off for a while on overload, and then it'll wait a few seconds and come back up again. So it looks like with this laptop going, charging full pelt, the 150 watt work light going, the Hacko running 70 watts, it looks like turning on the fan just pushed it over its 300 watt limit, and that went over the edge. This fan's about 50 watts, I think. So that's where we pushed it. But I'm going to see now if I turn off the soldering iron, for example. Let's unplug the computer. So we run the work light and the pedestal fan. Okay, so it seems pretty happy with that. Turn on the soldering iron again. Okay, and the computer. Yeah, there we go. So I am definitely pushing over the limit here. But you can see it's running a fair bit of stuff here, and that's all off of 1 car battery. So that little test there was a fairly mixed load. So we had the resistive light over here, the resistive load. We had the inductive load, which was this fan here. And we also got some sensitive electronics running, and yeah, it seems to handle it quite well. We did push it over the limit, and we could see how it handled the overpower state, where it sort of like shut itself off, waited a few moments, brought itself back up. But that was pretty good. So I'm hoping that it gives you an idea of what a 300 watt power inverter is capable of driving, and how much it took to sort of put it over its limit. Like I said, they do have the bigger ones, and they also have the smaller ones, so it just depends on what you're looking at running. And the easiest way to find that is just to get your equipment and have a look at the ratings. You know, this says 70 watts. So if you're going to plan to put one of these in your vehicle, or use it with a battery as an auxiliary power supply or something, that's something that you want to do. Sort of budget for the equipment that you're going to run on it. I've switched the laptop now for this oscilloscope again. This will give us the voltage waveform that the inverter is creating. This time we're going to test it with a load though, so we'll be able to see as we power on the light, the soldering iron, and I've still got this fan here as well, we'll see how the voltage output changes, how that waveform changes. So let me just set up the camera and get you a closer view of this, and then I'll run through some tests. Here you can see the waveform up close. There's no load switched on at the moment, so this is our previous waveform that we're familiar with. It's a nice modified sine wave, and I'm now going to switch a few things on. So first of all, I'm going to switch on the work light. You can hear the inverter's fan has just come on. You may also hear the oscilloscope's fan in the background. And you can see it's modified the sine wave a little bit here. We've got some slope happening on the upper and lower section of the waveform. I'll just unplug that and see how that changes. You also notice that the middle step shrinks a little bit, so it looks like we're going more towards a square wave when it's loaded. So this is a 150 watt work light. This is half load for this inverter. I'll now switch on the 70 watt soldering iron. This will take a second to kick in. We'll have a look at how this changes. So you can see, you might have noticed the work light just dimmed a little bit then, and also our max voltage is now at 276 volts, so the voltage output is dropping a little bit. Our volts RMS is still 246, 247 volts, so that still looks okay. Soldering iron's just clicked off again, so you may see it will start cycling. There it goes, comes in, off, on, off. So that's just the soldering iron modulating its temperature, and you can see what it's doing to the maximum voltage there. So we're now loading this up quite a bit. We're probably about 3/4 of the rated load right now. And finally, I'm going to turn on this fan. So we'll turn that on now. There's a pedestal fan switched on. Spinning up now, I can feel that breeze. So we're now at 252 volts RMS. Our volt max is 270, 280. And you can see that soldering iron still flickering on and off. So the waveform is approaching a square wave now. We're doing less of the 0 volt step here. I'm assuming that that's the way the inverter control circuitry is still giving us a decent volts RMS here, 250 volts RMS, even though our volt max is lower, 270, 280 volts, just because of the current that we're drawing now. So it's basically spending less time on 0 volts to just deliver the power that's required. But this does highlight this sort of wave here isn't ideal at all for an inductive load or for powerful motors, power tools, those sort of things. So that's just another look at when it loads up. It's even worse for those sort of loads. But again, you know, pick your appliances carefully. If you're worried about running motors and those sort of things, you've got a lot of those sort of loads, then pure sine wave may be a better option. But that's interesting nonetheless. So that's a look at the inverter's output under load. So thanks again for watching, guys. If you've got any suggestions for any further testing you'd like me to run on this unit, let me know in the comments below. Things like measuring harmonics or power quality and those sort of things we could probably manage. And also stick around for the teardown, which will be released soon. If you're interested in this product, it's available from Supercheap Auto. There's a link below in the description which will lead you to the product page. These things run around about $100 Australian, so it's a fairly decent price. And you can find it all in the description. Check out the links, and thanks again to Supercheap for hooking us up, and see you in the next video, guys.